power factor can be raised. And he also knows that power factor can be lowered. But he doesn't know how to do it. And I would guess that you don't either. As a matter of fact, do you even know what power factor is? You know what megavars are? Well, let's try to answer those questions. And to be able to answer those questions, we're going to have to start back again. And we're going to have to start with basic electricity. We're going to go back to a circuit that you've seen several times before, and we're going to talk about it for a little while. So let's get into it. The circuit I'm talking about is a simple circuit with a DC battery, and current is flowing in that circuit. And as you know, we commonly think in terms of conventional current, which flows from the positive side to the negative side. Now, in this case, the positive side is a long line on a battery, and the negative side is the short line. But what if we could reverse this direction continuously so that the current went back and forth? Well, we could do that if we put in an AC power source instead of this battery. Now, what happens if we had an AC source in here? Well, we'd see current first flowing in one direction, and then as the AC source changed, we'd see current flowing in the other direction. And that's an AC circuit. Now, if we plotted either the current or the voltage, we'd get the same kind of curve. And that curve is a sine wave curve, isn't it? And that's one cycle. But how exactly did we get that? Well, let's look back at a simple generator, and let's see if we can't plot one of those curves. Now, let's start out with a simple rotor, north-south pole, a single coil, and we're going to measure current this time because we've got an ammeter here, but we could just as well be measuring voltage, couldn't we? And we've got a load in there to get the current down so it's measurable by that ammeter. Now, let's make that rotor turn, and let's go through one complete turn of that rotor and look at our curve. First of all, as the rotor starts to turn and as the north pole approaches the coil, we're going to get up to a maximum voltage on our meter when that coil is right next to the north pole, isn't it? Then, as the rotor continues to turn, our meter is going to go down so that when the pole is vertical again with the north pole at the bottom now, our meter is going to be reading 0. And as we continue to turn that rotor, our meter is going to go down to its negative maximum when the south pole is right next to that coil. Then, as that rotor continues to turn, the north pole is going to get back up to the top again, and our meter is going to be back at 0. So that's how we got that curve. But we're not getting a slow cycle like that, are we? We're getting it real fast. As a matter of fact, around 60 cycles per second. And if we were trying to measure that negative and positive maximum, that needle would be going so fast that we couldn't even see what the voltage is. So we need some other kind of answer, don't we? Well, in actuality, these meters, both ammeters and voltmeters, are not measuring a maximum, they're measuring an average. For instance, if we read 110 volts on one of these meters, it's not measuring the maximum. That's not 110 volts maximum, it's 110 volts average. Now, the meter really is multiplying the maximum value by a number, and that's about 0.707. Now that I've said it, you forget it. That's not an important number because the meters already know that they're supposed to multiply, and they take care of it for you. So, we're all the time reading average values. Now, we still don't know what power factor is. We still don't know what megavars are, do we? But we're going to find out. Before we get into it, I'd like for you to review what we've covered thus far. So turn off the tape now read the first part of section A in your text and answer the questions. Well, let's now learn what power factor is. And to be able to understand power factor, we're going to have to go back to our same old DC circuit again, and let's solve a few problems. Let's assume we've got our DC circuit again, and current's flowing. We've got a battery that is 100 volts. We've got a resistor that's 5 ohms. Let's find the current. Well, you recall how to do that. It's pretty simple. Current is equal to voltage over resistance, or current is 100 volts over 5 ohms, and that gives us 20 amps. Now, what's the power in this circuit? You recall how to do that? Well, that's simply power equals voltage times current. And if we substitute those values in, we find that power equals 100 volts times 20 amps, or 2,000 watts, which we can also call 2 kW, or 2 kilowatts. Wasn't very difficult. But what if we change the circuit? What if we now put in an AC source instead of the DC source? Well, let's do it and see what happens. Okay, here's our circuit. It's got the AC source now. Does this resistor care? No. We find current the same way. And we find that the current, by the same calculation, equals 20 amps. And the power? Well, sure. The power we also find the same way. We multiply that out and we get 2 kW. So it doesn't matter. In that simple circuit, it doesn't matter whether it's AC or DC. And we call this a resistive circuit because it only has resistance in it. Now, that's a simple circuit. But we won't be reading something as simple as that in a control room, will we? And as you'll find out, we're not going to have a resistive circuit that our generator is supplying the power to. So let's look at some generator readings, and let's see if we can find some differences as far as resistive as compared to other kinds of circuits. Okay, here's our generator readings, and we can see we've got 15 kV, we've got 6,000 amps, we've got 72 megawatts, and 54 megavars. What's this? Well, let's do some calculations and maybe we can figure out what those megavars are, okay? Let's begin by trying to calculate power in the same way we've been working before. For this generator, which we're going to assume is single phase, power equals voltage times current, or 15 kV times 6,000 amps. Now, you just believe my math here, and you can check me later if you want to, but if you multiply that out, it comes out as 90 megawatts. So our instrument should be reading 90, wait a second, it's reading 72 megawatts. Hey, LD, is there something wrong with this instrument?
There's nothing wrong with that instrument.
Okay, I don't really understand that, though. I wonder why we've got that 72. Well, I'll tell you why. What we've just calculated was the apparent power, which we got by multiplying 15 kV times the 6,000 amps. And we used the wrong units. That wasn't 90 megawatts we just found. It was really 90 MVA. Now, that stands for megavolt amperes. So, what's our true power if that's the apparent power? Well, we're reading the true power right on this meter here. And what's that? Sure, it's 72 megawatts. And that 72 megawatts is what does useful work for us. That defines what the turbine is going to supply to the generator to get useful work out. Now, when we talk about true and apparent power, we need a way to relate the two, don't we? Well, we're going to use that term we've been throwing around, power factor. And we're going to define power factor as true power divided by apparent power. Okay? Now, in the problem we've got here, that means our power factor should be approximately 72 megawatts over 90 MVA, or around 0.8. Now, that's fine for this kind of circuit, and we know that this supply and these megavars and this system is not being supplied to a purely resistive load. If it was a purely resistive load, what would the situation be then? Well, we know for an AC or a DC circuit that we're going to get the same results if we do our calculations, don't we? And the true power in a resistive circuit is equal to the apparent power. They're the same amount, aren't they? So what does that make our power factor? Why, sure. In a purely resistive circuit, the power factor is 1. But in our system, the power factor is not 1. It's some other circuit besides a resistive circuit. And we need to find out what that circuit contains. And we still don't know what these megavars are, do we? Well, let's take a break now. You read the rest of Section A in your text and answer the questions. To be able to discuss reactive power, since we already know what the readings are, we need to find that missing link. And that's a missing link between megawatts and MVA. Okay, those are megavars, aren't they? Now, let's try to figure out some ways that we can better relate all those readings we were talking about that just don't seem to work out, do they? Let's try some addition. Let's say we added the real power, 72 megawatts, and we added the number of megavars, which was what, 54. If we added those, we'd get 126 MVA. But we know that's not true. We know we've really got 90 MVA. So that doesn't work. There's not a simple relationship, is there? Well, there is a relationship that you can understand. And to explain that, I'd like to talk about a friend of mine. Now, he's not from my hometown because he likes to go ice fishing. Now, when he goes ice fishing, he always takes a box so he can collect his fish. And on one particular occasion, he caught a lot more fish than he thought he was going to have. He did think ahead enough to get himself a set of cleats to put on his shoes so that he could pull them across the ice. Now, question here. Why did I choose ice? Why am I telling you this story? Well, ice has no friction, does it? So if we're pulling a box across the ice, we've just got to pull the weight of that box, don't we? Well, let's see how my friend solved it. He at first started pulling the box with a line that was horizontal to the ice. Now, from now on, the length of that line indicates the amount of force that he's got to use, okay? So he's pulling the box across the ice, but he gets tired of stooping over, so he starts to straighten up a little bit. And what do you think happens? He's got to pull harder on that box. He's got to exert more force to pull that box across the ice. Now, the actual force it takes to really pull the box, in other words, the horizontal force, is still the same. But now he's got a vertical component attempting to pull that box up off the ice. And that doesn't help him pull it any better. It hurts him. He has to expend more energy, doesn't he? and he's getting less useful work for the amount of energy he's putting out. Now, suppose he gets even tireder and he decides he's going to stand straight up and pull it. Well, that doesn't help any because he's got to pull even harder than before. And the amount of force he's exerting is even greater than before. And the reason for that is that his vertical component, the angle, the amount of force he's exerting to try to pull the box up off the ice is greater than it was before. So he's got to put out more. Now, that's a pretty simple example, isn't it? But that's very similar to the kind of situation you've got in your plant. If we compare all those readings, well, let me show you what I mean. Now, this horizontal line represents the actual useful work that's being done, just like as if you're pulling that box of fish across the ice. But the vertical component is work that doesn't help you any. That's the useless component. Now, this horizontal component we can call megawatts. That's true power. The vertical component is what? What do you think? You guessed it, it's megavars. They're not helping us any. And what's this one long line here? That's the apparent power. That's the power we would get if we moved the vertical line so that it touched the end of the horizontal line over here and made a triangle. Okay, we've got a triangle now that provides a relationship between those megawatts, the megavars, and that MVA, that apparent power. Well, let's plug our numbers in here and look at this. Now, if we plugged in the value for true power, we'd have 72 megawatts. Our value for apparent power was 90 MVA, and our megavars were 54 megavars, wasn't it? Now, if you work this out on some graph paper, you could see that those lines in the right length, you could figure out any one side if you knew the other two sides. But there's another way to do it, and it's an old math rule that you might remember, and it's called the Pythagorean Theorem. Okay, forget the name of it, that's not important. But that rule says that if we square one short side plus the square of the other short side, we'd get that equal to the square of the long side. Now, let's try that in this triangle that we've got. Okay, the square of the long side is MVA squared, and that equals the other two squared, both the megawatt squared and the megavar squared. And you don't worry about the math here, but just take my word for it. If you substitute in all those values, you get both sides equal to prove that that rule applies. Now, you're not going to have to sit in your plant and do all this. You're not going to be figuring up those triangles, but you need to know what's going on. You need to have an understanding. And we've got the basis now to start working with these megavars and find out exactly what they are, and we'll get back to what I said earlier, that bit about in phase. Okay? So you review what we've covered thus far, and then we'll get on with it. So turn off the tape, read the first part of section B in your text, and answer the question. Megavars. We've discussed them a good bit, haven't we? But do we really know what they are? Do we know yet? We can calculate them. We know that they don't really do any useful work for us, but they can hurt us. Well, let's investigate a little bit more. Well, let's try to really figure out what megavars are. Well, let's begin by analyzing the units, the MVAR. Okay, the M stands for mega. Well, you know what mega is? That means times a million, doesn't it? It's just a prefix. The V, that stands for volt. And of course, we got to have volts if we're going to measure power, don't we? The A, well, that stands for amps. And we got to have those to measure power also, don't we? But what about that last letter? That R stands for reactive. Now, that's the first time we mentioned the word reactive, isn't it? Well, reactive means that the component that is directly involved with those megavars reacts to changes. Now, maybe that doesn't make any sense. Well, let's look at a simple generator feeding a simple load. And let's say this is a reactive load. Now, by reactive in this case, I mean it can be called magnetic or inductive. What's an example of this kind of load? It would be a motor, and the motor coils, wouldn't it? Because those coils need magnetizing current before they can produce that magnetic field to make that motor run. But still, what do these megavars mean to that generator? Well, we got to have that magnetizing current. And as that current runs from the generator over to the load, it builds up in the first half of the cycle. In the second half of the cycle, that inductive load doesn't want anything to change, so it sends the current right back over again. And in the next cycle, current comes over to the load, second half goes back to the generator. So what's happening? Well, that current is just running back and forth and back and forth. It's really not accomplishing anything, is it? It's not doing any useful work. But hold on a second. There's something very, very important going on here. You haven't seen it yet, but you would if we now stick in voltage and see what voltage does because of this inductive load. Okay, back to our generator and load. Current is running back and forth, but voltage is also changing, and that voltage is not changing at the same exact time that the current is. They're all set. They're out of phase. And we have a very important fact. For an inductive load, current lags voltage. And how much does it lag voltage? Okay, it's a number we're just working with. It's by 90 degrees. Now, where did we see 90 degrees? Okay, sure. We saw it when we were talking about the relationship between megawatts and megavars, didn't we? There was a 90-degree difference. And that accounts for the difference between voltage and current. Current is going to lag the true voltage by 90 degrees. Okay, now that still doesn't really mean much to us. We know that's going on. What do we know about megavars? You know, so what if megavars are, don't cause, if they're useless power? If it doesn't cause any more turbine work, why should we worry about it? Well, there isn't any more turbine load involved. But there's something else going on. What's that? Well, we have a larger generator current now because of these megavars. And this larger current heats up components such as the generator, transformers, and switchgear. And because of that extra heat, our losses will increase. Now, that's not really acceptable, is it? Because we've got to overcome those losses to get the same amount of power out as we were going to get out before. Now, to be able to overcome those losses, what have we got to do? Well, we got to have larger components. We have to build larger generators, conductors, transformers, and switchgear. And our generator has to work harder because of those megavars, doesn't it? It's just like the man pulling the box of fish. He started getting overheated when he pulled at a greater angle, didn't he? That was more megavars. Now, what can we do about it? How can we know that we're going to be limiting, or how can we attempt to limit our megavars? Well, we can try to control power factor and get power factor as close to 1 as we can. Now, how can we say that more simply? Well, we want to get a larger power factor, which will lead to a smaller generator current, or in other words, we get our megawatts closer to MVA. And the larger power factor we have, or the closer megawatts are to MVA, the more efficient our system is. And we're constantly trying to do that, trying to get our system as efficient as possible. Now, you're going to be learning later on some of the things that can be done to try to make our system more efficient. But now I think you've got a better understanding of what those megavars are. They're something we don't really want, but something we've got to provide to enable motors, transformers, pieces of equipment that are inductive loads to work. Now, we'll be discussing more about inductive circuits, but you review what we've just covered about megavars. Turn off the tape, read the rest of section B in your text, and answer the questions. Way to start talking about inductive power is to talk about inductive circuits, isn't it? Now, in simplest terms, an inductive circuit is just a circuit that contains a coil that produces a magnetic field. Now, you've heard of that before, haven't you? And you have many typical inductive circuits in your plant. Now, examples of these are solenoids, motors, generators, and of course transformers. Now, inductive circuits have a peculiarity that does cause us problems from time to time, because inductive circuits will resist any change in current. Now, if that's what classifies something as an inductive circuit, I guess folks back home are inductive because they resist change too. But you've seen this before. Have you ever turned off your stereo and noticed that the sound from the speakers is just a bit behind in going down? In other words, you cut it off and then the sound dies out. It doesn't die off immediately. Now, one way of explaining that is to say that the applied voltage on the coil produces a counter EMF that opposes any change in voltage, and the effect of this is to supply a current that lags behind the voltage by 90 degrees and is out of phase of the voltage. Okay, do you understand that? Well, I didn't either. So let's explain it a slightly different way and go a little slower. I think we can understand it. Let's look at the voltage applied to a coil, and let's look at the inductive current that results. Okay, in the first quarter, voltage is going to build up, isn't it? And that voltage builds up to a maximum at around 90 degrees, isn't it? Now, in the next quarter of the cycle, the voltage is going to start decreasing. And as that voltage decreases, it gets down close to zero. But what happened to the current? Well, our inductors tried to resist that change in voltage, so current started flowing. Remember now, this is inductive current, and it's building up to a maximum as the voltage gets down to zero. But in the next quarter, as the voltage continues downward and starts to approach the negative maximum, what happened to our current? Well, since it's lagging behind, it dropped off too. And finally, in the last quarter of this cycle, as the voltage continues and goes back up to zero, the inductor is trying to resist that change. And the inductor will produce a negative maximum current now. Now, there's something very important here. If we now took those two curves and we superimposed them, what do you think we're going to see? Okay, you can see that the current is lagging the voltage, isn't it? They're out of phase. That current from that inductor is resisting the change in voltage. And again, that number 90 degrees pops up because the current is lagging the voltage by 90 degrees. Now, theory like that is not much use to us unless we can apply it. So let's try to apply it. And let's look at some simple circuits and do some calculations and see if we can't come up with that relationship with numbers. Let's begin with a very simple circuit, one that has a 100-volt AC source and a 10-ohm resistance. Now, it's a purely resistive load, isn't it? We find the current by dividing the 100 volts by 10 ohms, and that gives us 10 amps. And if we were to draw vectors or arrows representing the voltage and the amperage, they'd look like this. The volts and the amps are horizontal arrows, aren't they? Now, what if we want to calculate true power? Well, all we would do is multiply 100 volts times the 10 amps, and we would get 1,000 watts. Now, what's the power factor in this case? Okay, the apparent power is the same as the real power, isn't it? Because this is a resistive load. So our power factor would be equal to 1. Okay, that's a fairly easy circuit, isn't it? Resistive only. Now, what if we changed it so that now we have a purely inductive load, and suppose we changed it so that we have the same value of reactance. Now, by that I mean the units on that inductance. It's going to act something like a resistor as far as that power source is concerned. Okay, back to our circuit. This time we got our 100-volt AC source, but we've got a 10-ohm inductance. Now, how would we find the current here? Well, the same way as before. We divided our 100 volts by the 10 ohms, and we get 10 amps. And if we were to draw vectors for this, our voltage would be another horizontal arrow, but our amps would be a vertical arrow, wouldn't it? Now, it's common practice to show inductive current like this as an arrow pointing downward. And notice, there's our 90-degree angle, isn't it, between the voltage and the current. And what's the true power in this circuit? Well, we multiply again. We multiply 100 volts times 0 amps. And that's 0 amps because there's no real current. It's just that inductive current, isn't it? So our power is 0. And what's the power factor? Okay, there's no real power, so that's 0 also. Now, a couple of important points here. We had a purely inductive load and a purely resistive load, didn't we? We saw the range of power factor. 1 with a purely resistive load and 0 with a purely inductive load. Now, let's change our circuit again. And this time, let's take that 100-volt source and let's put 2 components in parallel. Let's put a resistor with 10 ohms in parallel with an inductor with 10 ohms. Okay, now here's that circuit. Now, let's find the current in each one of those components. First of all, the current through the resistance is 100 volts over 10 ohms or 10 amps. That was pretty easy. How about the other one? The inductor. Well, for the inductance, we have 100 volts over 10 ohms, and we get 10 amps, don't we? Those weren't difficult to figure out. But what's the relationship between those 2 currents? Can you figure it out based on what we've talked about so far? Well, I think you probably can, and I want to give you a chance to think about it. So right now, let's take a break. I want you to read the first part of section C in your text and answer those questions. Did you remember that relationship between the real and the reactive currents? Well, I heard somebody out there say, yeah, but for the rest of you, let's discuss that. Now, let's begin by looking back at our circuit again. We have our 100-volt source, we have our 10-ohm resistance, and our 10-ohm inductive reactance, don't we? And we got a 10-amp current through the inductor and a 10-amp current through the resistor. Now, this is how I would show them. They're 90 degrees out of phase, aren't they? Because one's real and one's reactive, inductive. Okay. Now, how can we figure an apparent current? In other words, the resultant of these two vectors. Well, we could take graph paper and connect the line and measure it, or we can solve it using that rule that I gave you for triangles. But what you would end up with was a current, an apparent current, of 14 amps. Now, let's go a step farther. How would we measure the power? Both real, the megavars, and the apparent. Well, as you can see, there's 100 volts across each one of those components, isn't there? So, if we multiplied this triangle by the voltage, 100 volts, we're going to get this. This is a triangle of power, just like we were discussing previously, isn't it? And now we've got 1,000 watts, 1,000 VARs, and 1,400 VA. Okay, do you see that? Just multiply the voltage times those currents. Now, look at this angle right here. Now, this is a measure of power factor, and it's sometimes called the lag angle. Now, so we've got a lag angle. Well, let's figure that power factor, and this is not essential that you know, but it's useful sometimes to know what the lag angle is. And let's figure power factor. Okay, the definition of power factor is true power over apparent power. Plug in those numbers, we get 1,000 watts over 1,400 volt amps, or VA. And if we divide that out, we get 0.707. Now, if you were to figure that lag angle, you'd come out with 45 degrees. Now, you're not going to have to figure lag angles, but you're going to see what a lag angle means in just a minute. But before we do that, let's look at lag angle if we drew curves, or in other words, sine waves, for that power. What would that lag angle, how would it show up? Okay, here it is. Here is one curve, and this is the voltage that was applied to 100 volts, and this curve is that reactive current, isn't it? It's actually a combination of both reactive and the true current. And you might call this our apparent current. And look at the relationship between them. 45 degrees out of phase, aren't they? Just as we saw the curve before, when we developed it and we were talking about theory. There's where that angle comes in. Now, let's keep going. Let's look at another circuit, and let's change our components. Okay, here's our circuit. Okay, we have a 100-volt source, but this time we've got a 20-ohm resistance in parallel with a 10-ohm inductance. We just increased the size of our resistance, didn't we? What kind of situation are we going to have now? Well, let's begin by looking at current again. First of all, the resistance, the current through the resistance is 100 volts over 20 ohms, and that gives us 5 amps. For the inductance, 100 volts over 10 ohms gives us 10 amps. Now, what's the relationship between these two currents, the real current and the inductive current? Well, sure, like we looked at it before. The 5 amps, the real current, is horizontal. In the 10 amps, the reactive current from the inductance is vertical arrow, isn't it? Now, what have we found a resultant of this? Okay, now If you worked out on graph paper, or if you calculated the right value, you get 11.2 amps. Now, let's go even farther. Let's make this current triangle into a power triangle by multiplying times 100 volts, and we get this. We've got 500 watts, our real power, 1,000 bars of reactive power, and our apparent power is 1,120 VA, isn't it? Now, look at our lag angle. It got bigger, didn't it? Well, let's calculate that power factor. Just as before, the power factor equals 500 watts over 1,120 VA, and that gives us a power factor of 0.446. And if we were to calculate the lag angle, we'd find that the lag angle is increased all the way to 63 degrees. Now, what's been going on here? What's the point? Well, I think you have a better feel now for how reactive power can affect you. And we've gone all the way from a purely resistive circuit with no reactive power. We discussed a purely inductive circuit where we have all reactive power. And we've gone to two circuits in between. As you saw, the larger our reactive current from that inductance, the smaller the power factor, didn't you? Okay, now I'd like for you to review this, because reactive power and what you do in a plant to correct it is very important. So go over what we've covered thus far. Turn off the tape, read the rest of Part C in your text, and answer the questions. One more circuit component, and that's the capacitor. Now, capacitors are important because they cause current to lead voltage. But I'm getting ahead of myself. Let's start with the capacitor itself. In simplest terms, a capacitor is simply a device that will hold a charge, okay? Now, capacitors are something that aren't entirely new to you. Basically, a capacitor is simply composed of a couple of plates in a circuit, and between them we've got an insulating material. Now, this insulating material has the ability to store a charge, something like a battery, okay? It's just something that will hold that charge. Now, there are many different types of capacitive loads that you could get on your transmission lines and through your distribution system. Some of the common capacitive loads that we could talk about are, first of all, radios. They're a pretty big capacitive load. And the air itself, and specifically the air between cables and ground, that tends to be capacitive. We also get capacitive loads as a result of the interaction between the cables and the sheaths around them. Now, we're going to discuss that a little bit more later on, but you remember that fact that those are capacitive loads. Now, what does a capacitor do in a circuit? Let's first assume a DC circuit, and let's look at a capacitor and see what's going on as DC voltage is applied. Okay, here's our circuit. Here are the two plates. And when DC voltage is applied, we get a flow of electrons that goes into the capacitor, starts to build up, and finally we get such a huge buildup of voltage in that capacitor that we get no more DC current flow. Now, this charge that's built up in the capacitor itself is a static type charge. Now, again, static charge is nothing new to you. If you've ever touched the front of a TV screen, for instance, that's static charge. as a result of normal operation of that TV. Now, that's fairly easy to see, I think, how it could build up the charge and then just stop the current flow. But we've got something else that can happen if we've got an AC circuit. Let's look at a simple AC circuit with our AC voltage source, could be a generator, and our capacitor. Now, let's look at the first half of the cycle of that AC generator. It builds up the charge in that capacitor. But as soon as the AC generator goes into its negative half cycle, what happens? This charged capacitor discharges in the same direction as the applied voltage. So the rush of current causes current to lead voltage. So as that capacitor is discharging, trying to oppose the change of the AC current applied to it, it's building up a charge in the other direction. So in the next cycle, in the first half, the positive half of the cycle, when the AC current applied again reverses, then the capacitor wants to oppose that. So it tries to pump out current in the other direction. So what's the net result of all this? Well, the net result is not only that that capacitor is trying to resist that change, but it's also causing current to lead voltage. Now, what are some characteristics now of a capacitive circuit? Well, a capacitive circuit allows the flow of AC current, but prevents the flow of DC current. And what was the result of having that capacitor in the AC circuit? Well, just like the inductor caused voltage to lead current, in the case of the capacitor, it causes current to lead voltage. That's just the opposite effect as that inductor, wasn't it? So that's a very important, vital point for you to remember. And as you'll see later on, that's going to be the basis. Those two facts, current leading voltage or voltage leading current, are very important facts in power factor correction. We'll get into that later. Let's see now if we can apply some of these rules, some of this theory that we've been going over to a circuit. And let's look at a fairly simple circuit. This will have a 100-volt source, AC source. It's got a 5-ohm capacitive reactance. And let's begin, as we always do, by finding current. The current in this circuit we find simply by dividing the 100 volts by 5 ohms, and that equals 20 amps, doesn't it? But how do we show the relationship between those amps and that voltage? Well, this time we show the current as a vertical line, and we show the voltage as a horizontal line. Now, look at these arrows. That arrow for current, and that's reactive current, isn't it, is now vertical upwards. But remember, for the inductor, it was down. But for the capacitor, it's up. Now, that's normal convention to show the capacitive load upwards. Now, what is the reactive power in this circuit? Well, we simply multiply the voltage times a reactive current. And that's simply 100 volts times 20 amps. And if we multiply that out, that would give us 2,000 VARs. Now, let's keep going, and let's put together what we know thus far. Now, this is very important because we're trying to sum up what we have covered thus far, and we're going to apply it in just a few minutes. Now, see if you remember this. For an inductive circuit, we have positive VARs, we conventionally call it, and I, the current, lags E, the voltage, doesn't it? But what about a capacitive circuit or a capacitive reactance? What's the case there? We commonly think in terms of negative VARs for capacitive reactance and current leads the voltage. Okay? Current leads the voltage. Now, you review this and make sure that you understand what we've covered up to this point, because in just a few minutes, we're going to put it all together and we're going to work out a circuit containing all these components we've been talking about. So if you need to, go back and review, but make sure you're ready. Okay, stop the tape now, read the first part of section D in your text, and answer the question. Let's now sum up all we've covered in this session by working a problem. And this will be a problem using all those components we've been talking about. We've got a 100-volt source, and in parallel with it, we've got a 25-ohm resistance, a 20-ohm inductance, and a 50-ohm capacitor. Now, this is the kind of thing you might have in your own distribution system. And these loads are going to be in parallel, aren't they? Let's analyze them. Let's look at each one and figure out what the power associated with each component is. And let's begin with the resistance. Now, first, we're going to find the current. We find that by dividing the 100 volts by the 25-ohm resistance to get 4 amps. And then to find power, we simply multiply 100 volts times the 4 amps, and we end up with 400 watts. And what kind of power is this? Sure, it's true power, isn't it? Now, how would we represent that? How would we represent that power? Well, we'd show it as 400 watts in a horizontal arrow, wouldn't we? That's for real or true power. Now, let's go to our next component, our inductance. Okay, in this case, we have the 100 volts divided by 20 ohms, or a 5 amp inductive current. And what's the power? Well, we do the same thing as before. We multiply 100 volts times 5 amps, and we get 500 bars. That's our reactive power for the inductance. And that's a positive 500 bars, isn't it? Now, how do we show this? Well, if you'll recall that 500 positive bars would show as a vertical arrow, but it's pointed downward since it's an inductance, isn't it? 90-degree angle to the real power. So we got a plus 500 going down. How about our last component, that capacitor? Well, for the capacitance, we take the 100 volts, we divide by 50 ohms, and we get a current of 2 amps. And to find the reactive power, we multiply 100 volts times that 2 amps, and we get 200 bars. But this is a negative 200 bars, isn't it? And how do we show that on our diagram we're originating here? Well, we show it as a vertical arrow, but it's pointed upwards, isn't it? It's a negative 200 bars from the capacitance, and that goes upwards, still 90 degrees from the real power. Now, how are we going to figure resultant? We've got 2 different bar numbers, don't we? Well, what we're going to have to do is take this 200 bars and find the resultant bars. Okay? That's pretty easy. All we do is, to find the net bars, we just take the 500 bars and subtract the 200 bars from it. And that'll give us a net of 300 bars. So now we've got something more to work with. Now we've got our true reactive power, this resultant of those 2. Now, graphically, we could just combine these 2 vectors, okay? And that's going to give us a resultant vector that's a somewhat smaller positive bars. And as a matter of fact, it's 300 bars, isn't it? Now, we get a resultant by graphically drawing a line between the 2 ends right here. And we could figure it on graph paper, or we could solve the triangle using numbers, as you've already learned how. And we find out that this is 500 VA. That's the apparent power. Well, let's keep going. How do we find power factor? Well, we know our apparent power is 500 VA, and to find power factor, we simply divide our real power, 400 watts, by our apparent power, 500 VA, and we get a resultant power factor of 0.8. Some awfully important principles were used in working this problem. They're principles you need to get accustomed to. Not because you're going to have to be solving problems like this, but so that you'll know what's going on, so that you can understand what reactive power is and what those megavars really mean. Now, one overriding fact here concerns power factor itself, and that is that efficiency increases as power factor approaches unity. That's very, very important. The smaller you can get those megavars, the closer you're going to get power factor to approach unity. And of course, that will give you your best plant efficiency. Now, you go over this material in your text. So turn off the tape, read the rest of section D in your text, and answer the questions.